So think about the art of economic modeling. So what are integrated assessment models? What kinds of issues are they designed to address? We've been talking about this, so I can go pretty quickly on this. Can they help us make better decisions? So any graduate students would probably want to learn how to do this thing. I cut my teeth when I was your age, I was working on merge. At that time, it was about 8,000 lines of Fortran code, and we were spending lots of time how to port it from one machine to the other. So merge was at that time it was called Ada Macro. It's a global intertemporal equilibrium model. It's very similar, even though Bill will always tell you that merge is really complicated and DICE is very simple. They're not all that different conceptually, in my view. Just merge has this back door where you can put lots of technology data in, but you don't have to. But it has this framework where you can talk about technologies, specific technologies that are available. But ultimately, at the core of the thing, it's really not that different in terms of a model. Now, there's this difference about how many regions are covered, but that's, in terms of the overall picture, it's not a big deal, big difference. And I'll get back to this on Friday, I guess. So you have in merge, you have this bottom-up engineering model that describes sort of natural resources and electric and non-electric energy. You have a top-down macro model. You have investment and capital accumulation, so it's forward-looking and intertemporal. Energy costs, and the key difference is you have these sort of magic numbers that show up in DICE that describe sort of the cost of abatement and so forth, and those basically come from the calibrated. My understanding is there's underlying that there's an elasticity of substitution of demand for energy that basically drives it, but here is more explicit. So the key differences we've seen is that intertemporal models of this type, there's trade-off between capital, labor, electric, and non-electric energy. You have the technologies, which is the key difference with this merge framework, and that describes macro production, which can be used either for consumption, investment, or energy costs. And then the key thing that makes it integrated is that you have emissions translated into climate, translated affecting welfare, through market, non-market mechanisms. And the key sort of idea here with technology, and this was, I guess, I didn't participate, but the EMF 27, I guess, which was undoubtedly, this is very similar in spirit to the WITCH model, this trade-off between traditionally technology assessment and integrated models of this type were mainly focused on how valuable it would be to society to have this technology available. You have a technology that has certain characteristics, how much carbon it uses, the capacity it has, various features about, you say, if we have that technology available, how much cheaper will that make it for us to meet a given climate target? It doesn't look at the question, so in the early studies, they didn't focus on the question of how much does it cost for us to put that technology on the shelf? That's not captured. Instead, you just say, well, if we have that technology, what will that do to the overall cost of integration? So what we're trying to do this week is to learn to think about how much does it cost to get that technology put on the shelf, and how do we assess that in connection with the other sort of aspects of the problem. So that's the basic sort of framework. So the key, one of my big sort of pet peeves here is this idea that key idea is cost-benefit analysis or cost-effectiveness analysis, but that's an equilibrium model that's operating underneath the hood. And I like to think about the model as beginning by first describing the world as we see it. So we want to have a model that describes investment decisions. And then my approach to this is usually think about, well, we have a set of instruments. We can't tell individuals how much they're able to invest or consume. We can only change a given set of policy instruments and see the outcome. So my view of the how to do this appropriately is not completely consistent with everyone who works in the climate problem, I'll just say. But we'll have a chance to get back to that later this week with a couple of examples. So, and that's really the difference between, I think about there being a positive model of how the economy operates, and then we may apply normative principles to evaluate different policy outcomes, but we use the positive model to describe how the instruments that we have that will change the allocation. Okay, and there's also this issue about how we incorporate multiple agents. I mean, on the last day on Friday, I'll talk a little bit about how to handle either multiple regions or also overlapping generations frameworks. So these are things that they're special sort of extensions. But again, you have to sort of trust me that If we can solve the optimization problem with one region, then we can basically accommodate more regions. And then the Geechee approach is one thing. This more recent algorithm, we have this sequential recalibration method. I'm quite enthusiastic about this. I think it has great potential. Because Negishi, the advantage of Negishi is you just have one optimization problem to solve, but you have to bring along with that all of the consumption levels of all the agents in the economy. So you have lots of dimensions in the model. Sequential recalibration does away with the agents. You just have one representative agent who buys goods, and just a matter of iteration. So I'll describe that on Friday. So the virtues here, explicit representation. Again, these are all, I'm repeating a bit of what Bill has talked about. Framework for assessing these things, explicit assessments of efficiency and equity. Logical appeal of sort of a general equilibrium model is, it plays well in a policy environment. You can talk about what's driving things with some care. You can identify, you can decompose exactly what instruments affect what agents, and so stakeholders can understand the consequences of things. I like the fact that it has this explicit representation of climate and technology and addresses issues of risk and uncertainty, which are central. The drawbacks. Oftentimes, the models are misunderstood or misrepresented. So, to start with, we don't really have a model of economic growth. This is essentially, these are what the Barrow-Salamartine framework would say, the book would say, these are all exogenous GDP models. I mean, there's a distinction between how much investment takes place and what might happen if investment were to keep up with labor, but we don't have a model that describes how fast will China transform. And if you think about the nature of the debate about climate, it's largely NX1 versus China. The debate, if we get China on board, then we can make a lot of progress, but China rightly is saying, well, wait a minute, what will this do to economic growth and transition? And we'll say, well, here's a model that shows you that this is good for you. And they look at the model and they're right in saying that model doesn't even address the issue that we're concerned about. Right? So the growth mechanism is something that's not in the model. It's, the assumption about the behavioral stuff, it's neat that we have a behavioral person here, David. I'm looking forward to learning more about this stuff. But, if we abandon the simplifying assumption of selfish optimizing agents, suddenly we move from being able to describe the assumptions of the model. For this model, go on the back of a postcard. You say, here are a few assumptions, run the model with the data. If you go to a behavioral model, a lot of times you have to have a phone book to describe all the assumptions you're making for special situations. So the complexity, the transparency with optimization is quite useful. So there's the basic challenge of this, of course, is that graduate education in this stuff is hard, and it's not been, the core micro foundations have not really been part of the PhD curriculum for 15, 20 years. And I like game theory, I think it's really useful, but organized price theory. You give somebody here's a well-designed, micro foundation problem, you have to learn how to think about how to go from the words to the model. It's going from what's the issue to what's the model to address the issue, and how you do that in a parsimonious way. That's the main challenge. And that's something that's not really taught very much. So this is Hell's Library. So Hell's Library is full of books of story problems, right? So that's a nice illustration. So here's a word problem illustrated. I didn't want to present this without giving you something to chew on. I posted the results, but if you have, like an agent, Thomas lives in Ann Arbor, currently spends 30% of his income on rent, gets an employment offer in Zurich that pays 50% more than his current income. He's hesitant to take a job because rental rates in Zurich are 3 times higher than Ann Arbor. So if Thomas has CES preferences with elasticity substitution equal to sigma, should he move or not, right? So a problem that it's like 2 sentences long, and it's the sort of thing we're economists, we should be able to think like this and do it like that. And generally my experience has been with students that this is the sort of thing that doesn't get taught that well, right? How to take the model from the small part of the book that talks about CES preferences, how do you operationalize that? And that's the whole trick with building structural equilibrium models, is this process of how do I think about the problem, how do I formalize it? And it's different than, for example, the answer to this problem can't be written down in closed form. You have to solve it numerically. But to formulate the model to get to the point where you actually can get leverage on that takes a way to think about it. So you can go through that of course, is all answering instant questions. The only good answer is it depends. And the key thing here is if the elasticity of sigma is equal to 0, then clearly he shouldn't move because it's a 10% loss in income. But if the elasticity is high enough, is willing to substitute, then he's willing to move. And you can go through that. So that's the basic intuition. I'm going to jump through the results because you can go off and look at that yourself. I'll give you one more problem because I have one more favorite one. So this is my latest version of this. I really like optimal dating. I like this problem is really good. So Jim has two girlfriends, Nancy and Louise. A date with either girl places demands on his primary resources, time and money, both of which are exogenously given. Dates with Nancy may be brief, but they're often expensive. Louise likes bike rides and canoe trips. Dates with her are not so expensive, but they require more time. He spends 1 hour a week with Nancy and 2 hours with Louise currently, right? So his relative money price of an hour with Nancy is P bar. This is the part about the problem I really like. Consistent with societal norms, we presume that Jim's preferences are concave, right? So then the question is, in the absence of a time constraint, he'd only date Louise. In the absence of a money constraint, he'd only date Nancy. So I'm going to say there's the preferences. I'll give you a little bit of a hint there. So the question is then, so there's a little bit about calibrated models. So there's a way of writing down, I'm big on how to use the CES function so you can take data that you observe and just immediately write down the model. You can just go, there's none of this business of I take the data and then I have to do all this black magic estimation. No, I just take the data and just write down the equations. And sketch the budget set, and then the question is what values are consistent and what values and so forth, and then compute the maximum level of concavity such that his preferences are consistent with behavior. So that's a little exercise. So the thing is, these sorts of things, the thing about model building is perpetually you're getting these little exercises thrown at you and how to figure out how to organize your thinking. I think that's a central part, one of the challenges for, in general, economic equilibrium modeling of all sorts. I mean, climate, trade, public finance, urban, any of this stuff, these sorts of problems always show up. Okay, so the key thing, the role of IMs in the policy dialogue is their framework for second-order agreement. Policy discussions can be focused, but it's important to recognize that having a model that promotes a particular policy proposal is a necessary but not a sufficient condition for the validity of that proposal. And so when you get into the policy game with models where you have interested parties on both sides, then it's important to bear in mind that it's okay to try to build a model to show one story, but then at the end of the day, the fact that you have a model, it means that at least you have that's a starting point, and it doesn't prove that it's necessarily true. And it's very nice if you can do some statistical analysis and come up with a range of sort of outcomes that's useful. So theory of the consumer, theory of producer, neoclassical paradigm. So this is the basic sort of story. I've sort of illustrated that. I personally like the neoclassical models because they tend to be somewhat, you can make things very, very tight, and Occam's razor. So theory should be as simple as possible, no simpler. Another thing is also a matter is these models tend to provide a better framework for doing out of sample. So if you want to extend, and that's one of the challenges with integrated assessment. A lot of times the agents, your clients are concerned about what's going to happen in 2050, and it's kind of, you have this tendency to want to actually tell them something, but if you tell them, well, the uncertainty range is huge, that's not always what they want to hear. Okay, so let's just I'm going to jump through this stuff. So let's get down to doing some economics. We had a question yesterday about relating this stuff to analytic models. So it's continuous time. So we have a paper I wrote with a postdoc. I had a postdoc who was coming from the continuous time domain, and he was saying he didn't understand why he should learn how to use numerical models. And so we wrote a little paper. We went through, we took a bunch of exercises from Kamian and Schwartz, and we wrote them out, did the analytic solution, then we wrote down the numerical solution. So you can see them side by side. So I put that on the distribution, so you can see sort of what you can do. Okay, so if we're building an intertemporal general equilibrium model, the first challenge is how to capture the fact that we can't solve a model that goes out to infinity. We only have a finite number of dimensions. So we have to think about how we approximate off the end of the model is rather important. And I'm a big fan of this, or the technique that I normally use is what's known as state variable targeting, meaning that you basically have a capital stock that's going to be at the end, and you come up with a method for setting that value, and you want to choose that value that you set will be such that the model moves approximately consistent with stationarity at the end. So the downside of this is you need to run the model out long enough that you're close to a steady state if you're going to get a tight approximation. But the upside is that it provides you the way of really avoiding terminal effects, which really is just a way, normally we don't have to worry. Computational overhead is not the issue. You can run dice, if you get it scaled properly, you can run it for 400 years. But if you want to put more into the model, so you want to take dice and you want to look at the effects of technology policy over the next 50 years, and what's the role, what's the appropriate scale and portfolio of investments, then you want to have more overhead in the model. So having the terminal approximation right is very helpful. So in this case, if we think about the subproblem for typical Ramsey models, we have a discount rate rho, and we have consumption C sub t. So you think about this as being, this is the accumulation condition says that the budget constraint for the agent says that the value of consumption over the infinite horizon has got to be equal to the value of the initial capital stock plus the present value of the wage earnings. Then you can define AT star as the terminal asset position. And that's going to be the difference between the present value of consumption, that should be a capital T, and the present value of labor income over the post-terminal period. That's how much capital, the value of the capital stock has to be at the end of period T plus 1, period T, to support the consumption profile over the infinite horizon. So suppose that we know that value. So if we know what a T star is, which could either be computed, so that's simply, you could compute that as the difference between, so you can do that calculation along the steady state, or you basically, just imagine we knew that. If we knew that value of AT, then you could partition the model, the infinite horizon model, into two parts. One part that goes through big T, and one part that goes from big T plus 1 out to infinity. So that knowing the asset position at that point ties the thing down and makes it possible then, if we know ET star, then we solve the T horizon model. We know we have exactly the same solution as you get from the infinite horizon model. So how do we determine that value? Well, this is the trick here is to go outside the optimization domain. That is, we're going to add something to the model which is relatively sort of seemingly innocuous. We're going to say we want to choose the value of the post-terminal capital stock such that investment grows with potential GDP over the horizon. So it says we're going to pick KT plus 1 such that investment from T minus 1 to T grows with potential GDP. It's just, this is completely just ad hoc, but it's going to be precise if we're at the steady state. So this all looks fine, but the problem is the key rub here is that you can't put this constraint into your optimization problem. Because if you put in a constraint like this, you'll pick up a shadow price in this constraint, which will distort the decision about the capital investment. In other words, in the final period, you wouldn't want to accumulate capital because that's going to cause you to want to have to make investment higher. So basically, this constraint is the constraint we want to have satisfied, but it's not something we can put into the model. And so that's, or rather, we want it to be a side constraint to the model that's done. So how do we handle that? Well, one way is you could, if you're solving optimization, you can iterate to determine KT plus 1, or you can solve the problem as a complementarity problem. So let's just mention about time horizons here. So the models that I'll distribute a few models. This is not the way DICE is set up, but normally the way, if I work with an intertemporal model, I usually think about there being, T is going to be the set of variables that are in which everything's endogenous. And there are two special elements of set T. One is going to be T, do I have a pointer here? So one is going to be TL, which is the last period, and the other is going to be TF, which is the first period. And then TP will be the period that's the first post-terminal period, because we're going to have to keep track of what's happening at that point for the capital stocks that are pushed off the end of the model. And then we have the big set TT includes all the time periods, including the endogenous periods and the post-terminal period. So that's the standard way we deal with time. So, okay, so that's one, so that shows, that's a bit, I'm going to come back to how we get this constrained in the model. I'll come back after I go through a couple of other things. Yes?
Why you can then start values that depends on the stock on capital or the stock of this AT?
What's that?
The scrap value in your criteria. So instead of having this.
The scrap value is, in fact, that is the value, that's exactly what the scrap value is. It's what the purchase price is of capital in the post-terminal period. So,
I don't know, but if you choose this function correctly, then you should not distort the criteria, the choice of the agent, because it's like an program.
yeah, but the thing is, choosing the value that you're going to assign to it is no different than choosing the value itself. You have to iterate to get it. The procedure I'm going to outline is one where I can set up my equilibrium model, hit solve, and it gives me back the approximate solution. I don't have to iterate. Okay, so the whole thing is to avoid, if you can, you'd like to avoid that approach. Yeah?
The parameter G, where does it come from?
That's going to be the growth rate of the labor of, it's an exogenous GDP model. The growth rate of labor and efficiency units is given exogenously. So typically, this is in the neoclassical model. So here, G will be determining the growth rate of this guy over time. So 1 plus G is going to be, at the final period, is going to be labor in the terminal period, the growth rate of that over the last period. Yeah.
So I have a similar problem with the finite time. What I do is when I discount, I just cut off the discounting and calculate the rest. If I would go to infinity, it's a sum, you can calculate it, geometric sum, and then I just use that as a weight for the last time step for discount. So the last time step usually it's a lot bigger than the discount before, so the last time step gets a lot of weight.
You know, that's the Mann-Bar algorithm. That comes back to a paper that Alan Mann wrote when he was for the Ford Foundation in India. So there's a paper and there's another nice paper by Eckhouse. Dick Eckhouse had a nice paper. So there's a variety of different techniques. This method, putting a higher weight on the terminal consumption period, that's another way you can do it.
How does that compare to this? Like,
The thing is, this method, my experience has been this method tends to be more robust. So it tends to be, if it's easier to predict how close you are to the study. My experience with this has been better. So that was part of the motivation for this sort of approach. Here I decided not on the first day to jump into the complexity, but the challenge in the integrated assessment model is not the capital stock. The physical capital stock is not the issue. More the problem is that the investment, the emissions that you do in the final decades of the model, they induce damages, if you're in a cost-benefit framework, that are completely off the end of the model. So the problem is that you have to, how do you get the emissions profile within the framework of the model to account for the fact that these have damages that extend out a long period. And I'll show you that at the beginning of next class. Here I just wanted to do, and we use a very similar technique where you can bring back what the effects are. In other words, we'll set up, so the version of DICE that I typically would advocate is one where you have the economic horizon going through 2100, but in fact you get almost the same results if you go through 2060, but then have the climate model going through 2300. So the horizon that's required for the climate is quite different than what you're, the economics does not, it basically falls back to a pretty stable growth path, but the problem is to bring back the damages from the post-terminal period into the model is the challenge. And this method is just, this goes back to a paper, this state variable card is JDC 1993, I think. It goes back a long time. So another issue. So what I'm doing at the beginning here is I'm just pointing out a few things where if you're the plumber and you're going to take somebody's equations and write down the model, this is what you have to know to do the plumbing, right? So the first thing to know about the plumbing is we have to worry about what happens at the end of the model. The second thing is how do we set up the model at the beginning to be consistent with what we see? That's what's known as calibration. I gave you those two little exercises, calibration. Calibration just always shows up in these models where you observe things, choices agents make, and you want to try to get the model to match that. And so benchmark replication is a standard sort of method in static general equilibrium modeling. And the idea is that if the model is parameterized on the basis of economic transactions and you have a set of policy parameters, then you should be able to check that the model replicates. And so in the original Chauvin-Wally analysis, this was always the big thing, is replication, verification of a static equilibrium. You can do the same thing in a dynamic model. This was basically, I would say, probably Dale Jorgensen was the first one to recognize this. He always would set up the model around a balanced growth path. And that way, you can set up a dynamic model, and if it's consistently operationalized, it should go straight through on a steady state. And so along the steady state, you have a condition for capital accumulation says that along the steady state growth path, if we have all prices decline with the interest rate. So PKT plus 1 is going to be PKT divided by 1 plus R, if R is the interest rate. So that says the capital price has to decline with the interest rate. And furthermore, the second equation says that the value of capital in period T is going to be 1 plus R times the cost of output in period. The price of capital in period T plus 1 is equal to the price of output in period T. That's because if you have an investment, there's a 1 period lag, you buy output, you get a unit of capital. So this is defining the capital price, and the base year price of capital is then 1 plus R prime. And then you have a zero profit condition for KT that determines the price of the returns to capital. So really there are two markets related to capital. One is the capital stock, how much it costs to buy the car, and the other is the capital rental price, which is how much it costs to rent the car for one period. And so if we own a car, if we buy a car at the beginning of period T, we get to rent that car out so that that capital purchase price can pay for the car, and then you have the depreciated value of the capital being passed forward to the next period. So this is the basic condition that ties down, that determines the price of capital. And putting these together, you can see that the rental price then is going to be R bar plus delta. It says the rental price of capital simply was the cost to rent the capital plus what you have to pay for rental and the time cost of the money involved in the capital and the depreciation. So this then, you put this stuff together, then you can see what the capital stock has to be, and then you basically have this condition that base year investment, I bar, has to then equal to K bar, that's the initial capital stock, times growth plus depreciation. So if we're on a steady state growth path, in the initial capital stock is related to the initial investment. You put this stuff together and you end up with this equation here, which is a condition that has to apply the economic data set, which is not typically imposed by the statistical authorities. It's simply statistical. If you produce input-output matrices or national accounts, they'll basically have adding up conditions that happen within the period, but they usually ignore what's going on across periods. So this condition is something that simply relates investment. If you're on a steady state, the value of investment is related to the capital earnings by this ratio of growth plus depreciation divided by interest plus depreciation.
Just a clarification. I don't know the macro logic well enough, but I understand that balanced growth plus is defined that everything grows at the same rate and so forth. Now, with the climate problem, we have a carbon stock that accumulates and, in optimum, at least for those models, falls. So what we're really interested in, and you interrupt me if I'm wrong, are off steady state.
We'll always be setting up the business as usual scenario. It will never be a steady state growth path. It's always going to be moving. But how do we set up, how do we parameterize the model, the parameters of the macro model in a top-down model? You have to set it up so that you take just the same way that we say we impose a growth path which is balanced at the end to tie down the end. It's the same way, if you're going to tie down the beginning, it's useful to know how far off you are. Because you want to have a model which kind of replicates what you observe. You want to solve the model and have the first year basically match GDP, investment, consumption, and that sort of stuff.
Consciously make a small mistake in calibration, but that's the best we can do.
Exactly. That's the reason I'm saying this is the art of it, is you have to pay attention to what's happening on both sides. Now, all of this happens when we go to DICE, all this stuff has already happened. Bill did this in his office very carefully when he set up the model. So the model we get already has this stuff built in. This is more if you're building your own model from scratch, this is the way you parameterize how to go back. Okay, so then, yeah.
So another way to do it, it depends on how you put it, you could do it through the savings rate, which I think is a little different. And
It's going to be the same. At some point, the savings, ultimately savings has to match investment.
yeah, no, but if the savings rate, it's actually a pretty natural parameter.
Okay, you can take the savings and then infer.
You can actually come close to calculating an optimal savings rate, and then you could just do that as in the terminal years. And actually, I sort of moved to that as a simpler way.
Yeah. Well, at some point, though, you have to parameterize the utility function. You have to know what the cost of capital is. You have to tie things down.
Yeah, well, wait, if you forget about the climate part, you can actually get an optimal savings rate as a function of the parameters.
Yeah.
And it's not quite right, but actually, as long as discount rates are not close to zero, it gets a pretty good solution.
Yeah.
It's another way to do it.
So then if we look, the final point, okay, so I've talked about terminal approximation. I've talked a little bit about calibration. And the final thing is this sort of remind you that this, again, is a piece from Micro, is that we can use a ordinary utility function can actually be, the CIES preferences can be written down this way as an ordinary CES function. The advantage of this approach is you get then an index which is an index of utility which is money metric. So that's, I mean, if you do the exercise up above, then you'll see what this is talking about. I mean, it's basically saying that the ordinary transformation that's not so crucial. Finally, you have this thing where we usually put labor in the model, but I won't worry about. Let's not worry about that. So this comes down to sort of. So this is looking at what's the Ramsey model, and so this is the infinite horizon model that you have. And now, how do we write this down? If we're gonna, so this is over an infinite horizon. So you can. It's not quite exactly the same as an NLP model over a finite horizon because n is infinite. But there's another problem class called complementarity problems, which involves weak inequalities. So here I have z is the central variable subject to lower bounds and upper bounds. Normally the lower bound is 0 and the upper bound is infinity. And then you have a function f of z, which is going to be related to these two slack variables. And because if w is positive, then f is greater than 0. If v is positive, then f is less than 0. But on a given component, whether it's positive or negative depends on whether the variables are on their bounds. So it's basically, if you think about this as sort of a Kuhn-Tucker system, then you get the idea. So I'll come back to this. Let's just write this down. So as an equilibrium problem, if you write down the basic sort of, it's the same, the equilibrium problem on the primal side looks very much like the optimization problem. You have output is equal to consumption plus investment. Labor is related to production in the given period. Capital is driven by the capital demand coefficient and the level of output. And you have these capital accumulation conditions that relate capital in period t plus 1 to capital in period t and investment in period t. So then, but you pick up on when you write down the problem as an equilibrium problem, you pick up a set of additional constraints, which are in fact the dual constraints. So these would show up in the optimization problem. If you solve this as a Negishi approach or as an optimization problem, these constraints are there, but they're the first order optimality condition for the variables in the model. So in the equilibrium formulation, you have a condition that says the price of output is equal to cost of production. Investment says that the cost of a unit of investment must be greater than or equal to the value of capital in the next period. And the complementarity implies that if the value of output exceeds the value of a unit of capital in the next period, then that's okay, but the investment has to be 0. The capital price relates to capital, again, this is the same condition. It says the purchase price of capital is equal to the rental rate plus the depreciated capital value. And then finally, we have this income balance constraint that relates the aggregate income to the value of the capital stock in that period and the value of the labor over the infinite horizon. And then finally, you're going to have a condition that's going to tie down the terminal approximation. So in some sense, I usually think about there being market clearance conditions. So an equilibrium model, the basic sort of rule is equilibrium model, typically 3 classes of constraints. One class will be market clearance, the second will be zero profit, and the third will be income balance. And then the final constraint, we have this auxiliary thing, which is how much capital do we have at the end? You have this terminal approximation. So we can solve this as an EMP, this extended mathematical programming method permits you to, you can solve this as an EMP by solving it as an optimization problem and then saying, oh yeah, and by the way, choose the level of KT plus 1 such that this holds. And so that's an EMP formulation, makes it possible to add a constraint. If I go back to what the EMP says, we're going to solve an ordinary optimization problem, f of x, subject to g of x greater than or equal to 0, but we want to basically perhaps add some variables with a balanced number of variables and equations, and we may want to have, in all of our equations in the EMP formulation, we may want to refer to the dual variables in the current problem we're solving. So the EMP formulation makes it possible to write down the optimization problem and the steady state condition without necessarily the two things that are not, you can handle, you can keep it as parsimonious as you would with a nonlinear programming formulation and incorporate the dual conditions, but it basically ties together cleanly. So there's the EMP model.
That went by me too fast.
Okay.
So how are you putting in the dual variables here?
So here, if you write down the nonlinear program, it says, forget about y and lambda first. Just think, maximize f of x subject to g of x. And think about, these guys are after the semicolon. So we think about y and lambda as being given exogenously. If y and lambda are exogenous, then we just have an ordinary nonlinear program. So in the EMP framework, you say, I want to, while I'm solving this problem, I want to add to that problem a system of equations. Right? And that system of equations will determine a set of side variables y. So in this example, the y, there's going to be one side variable, which is the terminal capital stock. And furthermore, I want to be able to reference those equations, those variables, y and lambda, during my optimization. But I want the optimizer to treat them as though they're parameters, not as decision variables.
You're going to show this, right? You're going to show
Yeah.
this? Okay,
So the thing is, you say, I want to have y and lambda be part of my optimization, but I don't want them to be, the optimizer just focuses over x.
so that you're then going to define y in terms of x?
Y will be defined by a set of equations that ties it down on the side. So if we go forward, so that this is basically, it corresponds to an equilibrium problem, but basically you can write down a problem which is in the Gishi camp with a set of side constraints, and automatically it will generate the equilibrium problem and solve it. And for optimization problems, this turns out to be a huge, for optimization problems, the terminal condition works pretty well, and this is just the first. There's several different situations where this is helpful.
Yes.
Yeah.
Doing the EMP, then I guess that you transform back your problem into KT conditions, and then you need to solve it with kind of a fast solver or something like that.
Well, the beauty of it, GAMS does this all in the background. So you write the model down.
Yeah, okay. Still,
And then
I
it
guess that you cannot go to kind of the complexity that you would be able to achieve with, I don't know, Canap or other.
Yeah, so if you're working in a world where you have a huge, huge model and you need to use, then you have to have another method. And typically, what that method, if you think about this sort of problem, if this is an equation that's on the side, you can just imagine so the normal method is just diagonalization. You fix y and lambda, solve the problem for x, take the lambda values back from the solution, solve the side constraint to determine what y is, and then proceed and do it again.
And can't you do some kind of iteration by looking at the dual variables of the equation and try to put it back into such that at the end you have a dual variable equal to zeros?
So the thing is, the diagonalization, you can diagonalize exactly, that's what the iterations would be. It's basically, you can solve this system iteratively. It's basically just, you have this technique, you can iteratively solve the thing, or you can do it simultaneously. Now, in the climate model, when you put in the post-terminal effects, normally you would do it iteratively. So you'd solve it and then have to put a loop.
So these Y are kind of .L things in GAMS. So they are not part of the optimization. Each iteration you have a new value and you put it back into your program.
Yeah, that's right. So you have this Y, in this variable, it's going to be KT plus 1. It's going to be this value. Right, so the NLP, and again, I put in a paper that's a short paper about how to apply the terminal condition with nonlinear programming where you do it iteratively. Which is normally, the thing is, if you're doing the Gishi model, you have multiple agents, you're iterating anyway. So you just do these updates as part of that process. Okay, so this is, I'm sorry, this is a bit heavy. I don't know. But the three things, I guess, just to recap, the key things that I think about for solving these dynamic models is the key thing is going to be terminal conditions and calibration. What's the third thing? And then terminal conditions and calibration. Oh, you also have this thing about how to write it down as an equilibrium problem. But typically, the relationship of the optimization to the equilibrium problem is something that's also important. But the basic thing is fundamentally to keep track of what's happening in the underlying equilibrium problem. Let's look at dice and see what this looks like. My objective today was just basically to give you a feeling about what was involved, and maybe it was not concrete enough. Let's look at the dice model to be sort of precise. So this is the dice with a few minor adjustments. So let's just look at the code. So rather than go here, let's go. So basically,
Can you increase the size of the letters?
yeah, let's just see here if I can do that. Say view, let's see if I can make this bigger. Is that better? I should have made it white. Let me see. Is that visible or not? Okay, I apologize for that. So the basic thing, what I wanted to do, my planning was not very good because I thought I was going to be using my machine, which is not bad. I don't know what the other alternative is here. Yeah, I don't know. Yeah, I apologize. This is not very good. Is that better? I don't know. Yeah, my intention was to go sort of live here and do a few things. I hope I can with this computer. We'll see. So the basic thing is you have a model. So the objective this week is to give you a sense about how to use GAMS. And the key thing to getting started with this is to be able to take someone else's model and run it and understand what comes out of it. And so what I wanted to do today, the first thing I want to do is just to show you how you can take a GAMS model and instrument it to generate output that you can then put into Excel and look at. So this is just a matter of how you compare across a set of runs. I'm hoping I can do this on this machine because I haven't even seen whether it has Excel or not. So here we have the basic sort of setting, and this is the same thing. If we look at what the changes were, mainly these are cosmetic, but these are things that the first thing, there's a small problem in the capital accumulation, but more the issue here is this actually turns out to be quite an important thing. When I write a GAMS code, I usually am careful to capitalize I capitalize variables and I lowercase sets and parameters. And again, that's just a matter that if you're writing a program, you like to be able to go back and read it and understand what's going on in that program without having to do a lot, without having to remind yourself of what is what. So if I look down here, so basically when you write down a GAMS model, you have a statement that defines a set. So in the GAMS framework, the set is the most important, so that you typically start by describing what are the sets you have. And here we say set T is going to be time periods, and it's numbered 1 through 60. Okay, so that's defining what the set of time periods are. And then we're going to define some parameters that go on. And this is mainly just cosmetic stuff, but you basically define the various inputs to the model are defined by giving a variable name, a description, and then there's a slash that gives you what the initial value is. And when it's not defined over a domain, there's no argument, then it's interpreted to be a scalar. So each of these is a scalar parameter that has one value. So it tells you, for example, T-step is years per period, and the description is separate from the, so you have the variable name followed by the description. So this describes all the various parameters that we have here, and then down at the bottom, after having declared what the data are, and you can't see, I guess you can see that these are, a number of these are parameters. Some of them, so most of these have initial values that are defined. And then you have a set of outputs. In this case, it's going to be what's the first, T first is what's the first period, T last will be what's the last period. You have T early will be the set of parameters that are the early periods, and then T late will be the late periods. And then we have a set of parameters that can be defined. And so once you've declared the variables, then you can make it assignments. And then so these are initial assignments that would be calibrating back what the various costs are. And then you have the declaration of the model. And so in this case, again, this is the same model, more or less, that Bill went through last time, that has the set of so the set of variables are both the macro variables and the damages and abatement costs, and they also have the variables that describe the climate model. So in a GAMS model, you declare the variables, and then you can declare certain models to be non-negative. So here we're going to say these variables are going to be bounded below by 0. And then you're going to declare what the equations are. And this, again, is not, this is just laying out what each equation are. And the basic sort of logic here in terms of being robust about doing is if you have the uppercase, the variables being in uppercase, and the parameters being in lowercase, then you basically have, it's easier to follow what's going on. So having declared all the equations, then you can define assigned values. And again, here, the robustness is going to be improved if you're careful about taking account for what functions are constrained, in other words, what the domain of the functions are. So you want to basically put lower bounds on things where if it goes to 0, the function can't be evaluated. So here we put lower bounds on the various aspects of the climate model. These are bounds that are, most of the bounds, some of the bounds are meaningful, but most of the time the number of bounds are just simply to avoid bad function calls along the process. And then we have an assignment to what the initial values are for the various parameters of the, so this is the initialization of the climate, the capital stock material balance. After having declared the model, then you write down, then you'll write a model statement. This is actually, the model statement is actually more, it simply says, put all of the equations in a model called CO2. And then we have the option statement is simply controlling how much comes out. So once you've set the model up, then the idea is that you have parameters that describe, what the inputs are of the model, and you have a set of equations. So if you think about the operation of solving the model, consists of, it's an instruction, if you say solve, what GAMS will do will be take the parameter values at that point and generate the equations, solve the model, and bring the values back to you. So basically, the solve operation is an operation on the database that says, go out, find the variables that solve, that optimize or equilibrium values for this problem, bring the values back. And so one of the challenges with GAMS is you would like to be able to run a series of experiments, and you'd like to actually say, go get these values, find the solution to this thing, bring the values back. And then the problem is, at that point, you want to look at them in some framework. And that's where GAMS does have limited ability for displaying stuff. That's where Excel provides a big advantage. In the Excel framework world, you can basically generate a set of values, which is, you can generate a set of you can generate a set of comparisons quite easily. So, but to get the stuff in a format that Excel can use, it's helpful to write to generate the solution, to have a report routine which can take the values from a given solution and save it for exporting to Excel. So here, I'm going to just declare a parameter called my pivot report. And each pivot report is going to be over time, so I'm going to keep track of all the values that come back from the model. And in my pivot report, I'm going to put in this, I have one special sort of, one special element of this is going to be this %1, which is simply saying that's going to be in my report, this report routine, that's going to be whatever argument I give. So it makes it possible to generate a database of solution values over time and have it be labeled for each of the scenarios that I run. So I'm basically writing a little subroutine I can call to invoke to save values into a routine. So if I go back to down, so that's just basically I've written a pivot report assignment that takes all the values back from the current solution and sticks them into a database. And then I can run a series of runs. And the first run would say, okay, well let's do the run with an optimal climate policy. And so to set up that run, you have to choose which ones do we want to, how do we want to set up the model. We put mu as the control value. We're going to put the lower bound equal to 0.01, fix the initial one equal to 0, and then we'll say solve using nonlinear programming. Once we've solved that, then we say that include report and label that particular scenario as opt. So we basically run the model, bring the values back, and stick it into that parameter. And so it's a little bit of programming technique, but it's one of these things is we have a model, we want to be able to run it with different assumptions and compare.
What's the mistake in doing about the people report?
The off echo?
No, not the above people report. This string one echo shows.
Okay, so it says, this is again, there's always a little bit of plumbing, right? So this is sort of plumbing. Here it says, I declare the parameter, that's in the main program, and then I say on echo v, means echo the following statements into a file, and echo v says do it verbatim. In other words, don't expand. If you didn't put the echo v, then the %1 GAMS will say, oh, you want the first parameter from the argument to this program. So echo v says, write me a file where you put the %1 into the file. So what this will do will be take this pivot report and write it. This will take these assignments and stick them into the side file, into the file, each of these assignments with the %1. I'm feeling a little bit exposed. I have to apologize because I didn't think about the fact that I couldn't hook my computer up. I'm accustomed to this sort of live demonstration is much easier if I actually can control things with the editor. So I will fix that for Thursday. So basically, you save everything out into the side file like that, and so that then makes it possible to take the results of the simulation and save them. And then it's a simple matter, once you've done that, to do a bunch more runs. You can do as many runs as you want to. Okay, so that basically gives you the ability to control what's happening. It all goes back, Bill, to the paper by Herbert Simon. It's the architecture of complexity. So it's this thing about computer bugs and programs and stuff. It's all about, you always have to be kind of consciously thinking about how to do stuff so you don't shoot yourself in the foot. And one of the things with GAMS is just that it's possible to do things so you can basically get it. It doesn't completely eliminate the scope, but I think you can get better than one error per 100 lines.
You have one catastrophic error.
Yeah, exactly.
When you have an error, it's a huge.
Yeah, although you have to, I'm a big fan of the pivot table approach because it makes you actually look at the numbers that come back. You can look at it and see what happens. So then once we've run this, then we end up getting, at this point, now notice I've done 3 runs. I've called 1 run, and notice that the call here, what I generated, I said generate the report and label that solution to be off. And then here I say generate report, call this one hotel, generate report, and call this one base. So I've generated 1 set of reports for each one of those guys. Once I've generated the reports, I unload the data file into a GDX file, which is again data exchange. It's a tight data file. Generate the pivot report there, and then at that point, I have to choose how I want to handle the data, and that's going to depend, unfortunately, on whether I have a Mac or a PC. How many people are using Macs? Okay, so I think Charles will be in charge of managing all the Macs on Thursday. So with the Mac, the basic problem is Mac was kind of not certain about whether they wanted to permit Microsoft to have access to running Visual Basic scripts in Excel. So in the initial version, they didn't permit them to do that. And then they decided lately that they would. GAMS hasn't quite caught up with the guy. Paul at GAMS has not caught up with that yet. So currently, if you're running on Excel, you can't immediately move the numbers from GAMS into Excel on a Mac, but you can move it as a CSV file. So this has got a statement that takes this GDX file and dumps it out as a CSV file that you can open. That's a text file that's Excel format. The other approach is you can write it, if you're on a PC, then you can execute this statement and immediately loads up the parameter. Now, the advantage of this, I'm going to try to see if I can, if you give me 2 minutes, I'll try to see if I can load this on this PC. Does this have Excel? I don't even know. Does it? But it's Italian, no doubt, so no doubt I'm going to crash and burn here, but I'll give it a shot and see.
Are you sure that you can't link up their computer to the...
You can we try this?
No, the problem is that it's used as it's a different plug. HDMI. I asked them at the beginning, they didn't have it. So
they don't have it?
No, they don't have it. So I'll fix this for Thursday. But let me just, so basically, if you have a, let me see if I can just pull out the...
Can I just ask, is this procedure documented somewhere? Because I don't remember seeing it. The pivot table, etc.
So the pivot table, there's a page on my website that describes how to interact GAMS. What I'm doing here is I'm just showing you a GAMS programming technique that can generate a database that you can pull into a pivot table.
So we go to your,
yeah.
Can you describe this?
Yeah, I can send around. The key thing here is that what I'm trying to do today, so the assignment for next week or for Thursday is that you should take the DICE 213, put it on your computer, load a copy of GAMS, run it, and generate and pull the stuff back into a pivot table. That's the objective. Now, so the point is that the running the model, and that's the thing, the running the model, the main objective is that running the model should be nothing, because you should be able to solve that. But I can help you with that if there are problems. But between now and Thursday, I'd like you to take the model, put it on your machine, and run it, and generate the output file, and generate the pivot table. Now the pivot table stuff, that's something there's tons of documentation for how to do this on the web. So you can find, on YouTube, you can find instructions on how to do that. Again, I'm happy, or Charles is happy to help with getting that, with organizing how to do that. I was hoping today that I could actually do it on my machine, but let me just, if you give me 2 seconds, I'll see if I can do this. I don't know why it doesn't split it as a, but if I see it here, data, text to columns, I say delimited, next, delimit it with a comma, and I say finish. That gives me my values, and there's all the numbers. Are these guys saved as, okay, so this is going to be the scenario, this will be the item, this is going to be the period, and that's the value. So here I'm showing you something that's this basic sort of pivot table technique, right? Which is how to work with, if you have indexed, it's fundamentally, we're always interested when we run numerical models We're interested in how does it depend? How do things matter? What matters? And so the process of generating a pivot table is just a way to interrogate your model to find out what comes back. So so in Excel, you can say like this, and then you say, let's see, insert. This is Excel 2007. I can say pivot chart. So I've highlighted the columns that have the values in them. I pick that range. I say, create a pivot chart from that. It says yes. Then I grab the values and I put those into this box. And I have to be, there's a bit of, so this would be, say, sum. And then I put this guy into this box. And then I say, well, let's look across scenarios and let's look across items. So now I've set up my pivot table with the values. And I can move the chart to be in a new sheet called, say, my pivot chart sheet. And then I can say, at that stage, I can say, let's change the chart type to be a line chart. And then let's go here and say, well, what item do I, here it's looking at all the items. What's a good one to say? Carbon price, C price. Oops, we have to have a variable here. Let me just go here. It's going to say, what is going on here?
I guess it's because of the regional specification between the point and the commas.
Yes.
Oh,
So international settings there.
Options?
is there a way? I don't know how to change it. So I'd say, Excel options. Well, I can re-import the data though. So I'm going to say region. Oh shoot.
I think it's advanced.
Advanced. This guy.
System support.
So the decimal separator is going to be the 1.
Yeah.
And I can say insert file. Does somebody help me? I don't know how to do this. Let me just see. That'll just, well, that setting will be saved just with this file anyway. Yeah. I don't know how to do this. That's got the.
I think it's already done. It's already done. It's done it, but maybe then we should report it
Can you
again.
change it to number?
Is this guy not saved this number? Anyway, I'm not sure.
I think you should report it again. I think when we did the comma separator, we were.
So I say
If you go to data,
data.
then you select column D and you say select column D.
So what do I do? Where do
Select column D.
I select from?
And then first you select column D, and after that you say text to columns. It's a button somewhere.
Oh, I see. It's kind of above all.
Text to columns. It's called. It's on the
Text.
right in the middle. Yeah.
No, but that should be. I don't know. But it's screwed up my numbers.
No, you don't.
Yes.
So I have to re-import the file. I think.
You can do that. It's no problem. I'm sure. It's no problem.
So let's say if I say open this file.
Text to columns, and then you can place what kind of separation.
Save as. It's very bad to be demonstrating software and to be. I assure you, on my own machine, I'm competent. I don't know. I'm afraid.
That's not the point about using Excel, right?
Yeah. I mean, the point is just to show you what you've done is you can. Let's just see if we can do this one more time. So if I say file, close. And then if I say file, how do I import an Excel file or a CSV file? E.
Who's there? Wait. That's me.
And then as
Quiet time.
Okay, it's pivot report, not the right one. And now you should open it correctly, and now you should, yes, now it sees correctly.
It's right, okay, so this is scenario.
You need first to do
Item,
the
period.
separation. Without
So if I say like this, I say
yeah,
data.
now it's
Okay, so now I've got the whole thing, then I just go like this. I say insert pivot chart, say yes, value there, put period down here, put item right here, and put scenario right here. And then if I say, default is it takes the values to be the count of the number, so you have to set the values to be sum. And then if we say move chart, and then if we say change chart type, make it into a line, then you can change the item to be what item you want to look at. Say damages. And then that's looking at the damages in those two scenarios. So basically it then gives you the ability to move between, you can look at carbon price across scenarios. And that's getting, you basically have a method of relatively easily picking between. And what's more, what I like about this use of Excel is that you can import, if you run the model again, you can import the data right on top and then say refresh. And so what you've set up here can be refreshed and automatically reloaded. So it has advantages for looking at stuff. If I look here, now one thing that's helpful, you could say, so it looks like B1, so I could say, for example, here, layout, chart title above, and that could be and then you could look across different items. So just, I realize it's a little bit mundane, but the idea here is we want to be able to solve a bunch of different models, and I'd like to try to make it, I realize that in the space of 1 week you're not going to pick up GAMS perfectly, but I'd like to have a set of models where we can look at the results and do some runs and change things. And the Excel interface, learning how to run a pivot table is something that's useful for other reasons as well. So if you could do that for Thursday, I'm happy to be of service, and Charlie, I'm sure, can help out as well.
I don't believe you've gotten the temporary license code yet.
The temporary license code is they'll distribute, so the flash drive for the course will be distributed at lunch, and it has, I have a OS X, that's for Apple, Windows 32 and Windows 64 versions of the code. It has the GAMS license file, which is good for, I don't know, 3 or 6 months. And then it also has, I also got an evaluation copy. For those of you who are using Apple, I've included a text editor if you want to use it, Epsilon, which is normally what I use. It's like an Emacs style editor. I got an evaluation license version of those. And so that has everything that you can load. The Apple one, let Charlie help you. There's a piece of code, anyway, so make sure you get that installed. The Apple ones probably could use some tutorial help getting started on how to use that. So if you can handle that, that would be helpful. And on the Windows stuff, I'm happy to answer questions. So the main objective is, I'd like to get to the point where we can give you a model and then you can run it and then we can compare things across different scenarios on Thursday. So the objective now is just to make sure, let's get to where we can run the GAMS program operational, and then we'll shift. So just to recap, what we've done today is I basically went through the basic, so some of the subtle issues involved in setting up integrated assessment models. We talked a little bit about what the challenges are. We went a bit through calibration, and the basic objective for Thursday then will be to think about what happens when we take this deterministic forward-looking model and how do we incorporate states of the world into it. So the idea is to generalize this so we can talk about it. The technique that we'll be learning about is the method that you can take an arbitrary event tree and put it on top of the deterministic model. Okay? So, And then I'll also talk a little bit about, I have a very simple little learning model that has Bayesian learning, so I'll show you how to do that in the GAMS framework as well. So on, okay? So that's it for today.